We are Group 13, and today we are going to present a paper which is memory cache GPU scaling up and out key value stores. The authors of this paper are Taylor, Mike, and Tom, and the paper is presented by Lijong Chen
and Baden Delma. The overview of this paper will consist of the motivation, the design and main idea, which will further consist of a short background, an introduction on genome architecture, and details about memory cache GPU. And to close, we'll have the evaluation and the conclusion. Motivation behind this paper is a rather practical one. It involves data centers. For those that don't know, data centers contain large numbers of servers, memory, network hardware, non-volatile storage, and cooling that when put together can consume tens of megawatts. Reducing energy consumption is therefore a key concern for data center operators. Now, US data centers can use more than 90 billion kilowatt hours of electricity each year. And these data centers can use 416 terawatts just in 2016 alone. To put that into bigger scope, that is about 3% of total electricity used. This consumption every 4 years will actually double. Now, these data centers are also responsible for about 2% of total greenhouse gas emissions, which is around the same carbon footprint as the airline industry. The 416.2 terawatt hours of electricity the world's data centers used was significantly higher than even the UK's total consumption of about 320 terawatt hours. Now, the problem addressed in this paper involves the efficiency of data center computing. We need to maintain low latency, low cost programmability, and the potential for workload consolidation. Now, how do we implement this? We need to implement and evaluate an end-to-end version of the memory cached, which is a distributed in-memory key value caching device, or service rather. Memory cache GPU on commodity GPU and Ethernet hardware. We need to develop a complete system, genome, that incorporates UDP network processing on the GPU in line with the application processing. Now, genome will provide a software layer that will provide efficient management of the GPU tasks and network traffic communication directly between the network interface and the GPU. Now, the following are related works and incremental solutions, FPGAs and the GPU net. First solution is the FPGAs. Other works have considered using them because of how well they accelerate memory cache. While the FPGA architecture enables high energy efficiency and high performance, the flexibility of the general purpose GPU architecture may outweigh some of the efficiency gains in the data center. While FPGAs can provide high levels of efficiency for a single application, the long reconfiguration times on current FPGAs may mitigate some of these benefits. This is at odds with improving efficiency through higher utilization by consolidating multiple workloads on a single server. So the two main issues with FPGAs are flexibility and long reconfiguration times. Now, GPUNet is the second solution. It's a networking layer and socket level API for GPU programs. Similar to Genome, GPUNet actually aims to improve the support for applications requiring networking I/O and GPU accelerators. However, GPUNet is designed for InfiniBand hardware and is directed towards more traditional GPU applications, such as image processing and MapReduce. The current cost of InfiniBand hardware is a very large contributor to the restricted usage outside of HPC. But the Genome will actually target commodity Ethernet hardware that's typically used in data centers and will evaluate a non-traditional GPU application called memory cached. Now we'll go into the design and main idea set forth by the authors of the paper, and we'll start off with the background, genome architecture, and end with the memory cached GPU. Now for the background, memory cached and the network interface architecture are the two more important ideas. Memory cache is a general purpose scale-out in-memory caching system that's used in distributed database systems. They're used to improve performance by reducing the amount of traffic to back-end databases. Memory cache is actually used by many of the popular network services that we all use, such as YouTube, Twitter, Facebook, and Wikipedia. Memory cache can provide a simple key value store interface to modify and retrieve data from the hash table. The NIC architecture will connect to the host via a PCI bus. The NIC then will send an interrupt to the CPU for one or more pending RX packets. The NIC driver will then copy the packets to Linux socket buffers and returns the RX buffer back to the NIC. Optimizations such as direct NIC access may reduce memory copies by allowing applications to directly access the RX buffers. The GPU architecture. GPUs are throughput-oriented offload accelerators traditionally designed for graphics. The recent GPUs we know are capable of running non-graphics applications that are written in C-like languages such as CUDA, which is the language the author uses in his paper, and focuses on discrete NVIDIA GPUs connected to the host device through PCI bus. CUDA applications are typically composed of two parts, the host side and the device side. The host side will be responsible for initializing the GPU's environment and communicating with the GPU, while the device side, which executes one or more kernels. A CUDA kernel, furthermore, is a user-defined parallel section of code that runs on the GPU. Now, the contributions made by the authors in this paper make the following. The contributions made in this paper present Genome, which is a software system used for UDP network and application processing on GPUs, and evaluates the feasibility of achieving low latency 10 gigabit Ethernet line rate processing, all request sizes on commodity Ethernet and throughput-oriented design. The other contribution is the memory cache GPU, which is an accelerated key value store which leverages Genome to run efficiently on a GPU, and it compares memory cached GPU against prior memory cached implementations.
Okay, so now I'm going to talk about the Genome software architecture. So first of all, I'm going to talk about request batching. And request batching in Genome is done per request type in order to reduce the control flow divergence among the GPU threads. And the paper finds that 512 requests per batch provides a good balance of throughput and latency. So the software architecture of Genome. Genome is composed of two main parts that work together to balance throughput and latency for network service on GPU. And the first part is Genome host, which is typically CPU. And it is responsible for interaction with the NIC and pre-post GPU data and task management. And the second one is Genome device, which is responsible for UDP packet and application processing. So the Genome host is required to provide task management and I/O support for the GPU because currently the GPUs cannot directly communicate with or receive interrupts from the NIC. And the host is composed of three software components. And the first one is Genome ND, which is an Intel network driver. And the second one is Genome KM, which is a Linux kernel module. And the third one is a user level software framework, which is Genome user. So the Genome device leverage additional helper thread to perform parallel tasks related to a single network service request, which explodes both packet level and task level parallelism to improve response latency. So now we can see that it is the graph of the Genome software architecture, and we can see in the first part of this graph that the RX packet actually goes directly to the GPU memory using the GPU direct. Using this method, we can reduce the RTT latency, and only the metadata will go to the CPU. And the lower portion of this graph is to illustrate the CUDA kernel for UDP packet and network service processing. So now I'm going to talk about memory cache GPU. So the data structure used by memory cache is both get and set request. And request include a hash table to store pointers to memory cache items. And we place the hash table containing keys and item pointers in GPU memory, and values remain in CPU memory. So the main get request operation on the GPU and all of the memory cache data structure accessed by get request are stored in GPU global memory. And the set command request requires spatial attention to ensure consistency between CPU and GPU data structure. um, so the set request first allocate the item data in the memory cache, the memory slab in CPU memory, and then update the GPU hash table. So why this ordering is important? This ordering ensures that the subsequent GET requests are guaranteed to find valid CPU item pointers in the CPU hash table. So I'm going to talk about hash table design. So the traditional baseline memory cache implements a dynamically sized hash table with hash chaining on collisions. So this hash table resolves collisions by dynamically allocating new entries. But this method is a poor fit for the GPUs for two main reasons. First of all, the dynamic memory allocation on current GPUs can significantly degrade performance. Secondly, hash chaining creates a non-deterministic number of elements to be searched between requests when collisions are high. So it can also degrade the efficiency. So to solve these issues, memory cache GPU implement a fixed size set associative hash table, and the authors did at a size of 16 ways. So the GPU concurrency control is also very important in this paper. Aside from updating the timestamps, GET requests do not modify the hash table entries. However, the set request will require exclusive access because they modify the entries. To solve this problem, we employ a multiple reader, single writer spin lock for each hash set using CUDA atomic compare and exchange. So we are going to cover the evaluation part of this paper. So first of all is the methodology of the experiments. So all of the experiments are run between a single memory cache server and the client directly connect using two Ethernet cables. And we can see that the main system configuration is presented in table 1. So the GPUs evaluated in this study are shown in table 2. And they all use CUDA and so the first one is the high performance NVIDIA tester, and it is evaluating using GNUM, which support the GPU Direct. And the lower power NVIDIA is evaluating using non-GPU Direct. And the memory cache GPU was implemented from memory cache of this version and is configured as a 16-way set associated hash table. So here's kind of the evaluation of this paper. So first of all, we are going to talk about the throughput of the experiments. So the packet trace of 500 million requests with equal length keys at peak throughput and averaging over 3 runs. So the data presented in this table is more reliable. So we can see that a memory cache GPU is able to process packet near 10 gigabyte rate for any memory cache request size with server packet drop under 0.006% for GNOM software architecture. So then we are going to measure RTT latency. So the left graph is the mean of the RTT, and the right one is the 95 percentile of RTT for a test up with GNOM and NGD, and also Maxwell with NGD. So we can see that in either graph, the Tesla with the GNOM software architecture achieve a lower latency than NGD. So finally, we come to the energy efficiency graph. So we can see that the Tesla, which use the GNOM software architecture, and when the throughput comes by 13, multiple by 13 times, the power increase by less than 35%, which leads to the steady increase in energy efficiency. So the conclusion of our presentation is that using GNOM software architecture, memory cache GPU is able to achieve 10 gigabit line rate processing at all request size, and using only 16.1 mu geo and of 1.1 milliseconds on a high performance NVIDIA Tesla GPU. So we believe that future GPU-enabled systems, which are more tightly integrated with the network interface and less reliant on the CPU for I/O, will enable higher performance and lower energy per request. Overall, we demonstrate the potential to explore the efficient parallelism of GPUs for network-oriented data center service. So thank you. That's all for our presentation.